Last session, we talked about the heat change and calculations which we can do from the temperature change. And we find the relationship between the amount of the heat, the mass of the object with heat transfer into it or transfers out of it, and also it depends on the specific heat capacity of a substance which is special for any type of material, and the temperature change which happens in that amount of subject or mass. And we said the amount of the heat can be calculated from the mass times specific heat capacity times temperature change of that substance. The definition of a specific heat capacity was given here. So the specific heat capacity is a property of a substance. So for different substances, you have different specific heat capacity. Is a property of a substance which gives the heat needed to increase the temperature of the unit mass by 1 Kelvin. So the amount of heat which we need to increase the unit mass that we use in chemistry is gram here for a specific heat capacity. So this amount of the heat which is needed to increase the temperature of 1 gram of any substance by 1 Kelvin. And because 1 Kelvin change in temperature equals to 1 degree centigrade change in temperature, you can use them interchangeably. Okay. So, but we have another concept, and it's heat capacity, not a specific heat capacity. Look at the amount of the water which you have inside this swimming pool and inside this kettle. Both of them, the substance is water, and the specific heat capacity for the water is 4.18 joule per gram per Kelvin. It means if you want to increase the temperature of 1 gram of water by 1 Kelvin, you need 4.18 joule amount of energy. This is a specific heat capacity of the water. But the heat capacity also considers the mass. Although these two substances are water, but their heat capacity is different. Obviously, you need more heat to increase the temperature of the water in the swimming pool because its mass is more than mass of the water which you have inside the kettle. So you can say that heat capacity of a swimming pool of water is more than heat capacity of the water inside the kettle. Definition of heat capacity is given here. It says the heat capacity is defined as the heat needed to increase the temperature of an object by 1 Kelvin. So what's the difference between definition of heat capacity that we have here and definition of the specific heat capacity which we had here on previous page? You can see in the heat capacity, it's not mentioned for unit mass, but for specific heat capacity, we mentioned the amount of heat which is needed to increase the temperature of unit mass by 1 Kelvin. Here, we just said the amount of energy we need to increase the temperature of an object by 1 Kelvin. So, heat capacity also considers the amount of the mass of the substance. Actually, the heat capacity is multiplication of the mass by a specific heat capacity. If you multiply these two by each other, you get heat capacity, which we show it by capital C. Specific heat capacity is shown by lowercase. So that's why if you want to rewrite this equation based on the heat capacity, you can write the amount of heat is heat capacity times temperature change of that substance. And if you want to find the heat capacity, you can just rearrange this equation. So the heat capacity is the amount of heat which transfers to that substance over the temperature change of that substance, which is given here. So from this equation, you must know what is the unit for heat capacity, because the unit for the heat change is joule, it's energy, and the unit for the temperature change is Kelvin. So heat capacity is joule per Kelvin. But specific heat capacity, it was joule per gram per Kelvin. So there is difference between unit of heat capacity and specific heat capacity as well. The definition and the formula for both of them are given here, so you can easily find them in your text. And one more important note which we mentioned earlier, we said the change in 1 Kelvin is equal to change in 1 degree centigrade, so we can use them interchangeably. Okay, let's do one work example to be more familiar with this equation. It says how much heat is released when 10 gram of the copper with a specific heat capacity of 0.385 joule per gram per degree centigrade is cooled from 85 to 25. So the point is that here it says how much heat is released. And how do you know the heat is released? Because the temperature of your subject is decreased from 85 to 25. So if you have a block of copper and the mass of that is 10 gram, if it loses the heat energy, its temperature decreases. So is this process endothermic or exothermic?
Exothermic.
It's exothermic, yeah. So let's find, because the heat is given out from the system. Let's find the Q for that one. So the Q equals to the mass times the specific heat capacity times delta T. The mass of the object is 10.0 gram times the specific heat capacity is 0.385 joule per gram per degree centigrade times the temperature change, which T final is 25, T initial is 85. So final minus initial, 25 minus 85. And the unit is degree centigrade. Okay, so if you multiply all of them, you get this answer. Negative 231 joule. Where this negative comes from? Actually, that comes from here. The delta T is final temperature minus initial temperature. Because the final temperature is less than initial temperature, this parenthesis becomes negative, and the overall answer becomes negative 231. And the unit is joule. You can see that this degree centigrade cancels this degree centigrade here. This gram cancels this gram here. So only the joule remains here. And the sign is negative. Again, the negative value emphasizes that this reaction or this process was exothermic. So pay attention to the signs and how you write the final temperature and initial temperature here, because it's very important. It can change your answer. One more thing that I want to add here is the number of the significant figures which we have here in the answer. You know that we are multiplying several quantities, and when you are multiplying several quantities, the number of the significant figure in the answer must be same as the number of significant figures in each of the quantities which you are multiplying by each other. But in this parenthesis, you are subtracting two quantities. When you subtract two quantities, the number of the decimal point in the answer must be same as the number of the decimal point in the number which has smaller decimal points. Both of 25 and 85, they have one decimal point, 0.0, 0.0. So if you subtract these two from each other, the answer would be 60.0. Okay, because the number of the decimal point here must be same as the smallest one. Both of them has one significant figure. Now you are multiplying these numbers. 10.0 has three significant figures. 0.385, it has three significant figures. 60.0, it also has three significant figures. That's why the answer is rounded to three significant figures. Let's move on to the exercise that we have here. Let's answer each one of them. Question number 1 says, when a sample of NH4SCN, it's ammonium thiocyanide, is mixed with the solid BaOH2 8H2O, barium hydroxide octahydrate, in a glass beaker, the mixture changes to liquid and the temperature drops sufficiently to freeze the beaker to the table. So what happens to the temperature of the surrounding? The temperature of the surrounding is decreasing. Which statement is true about this reaction? Is it endothermic or exothermic, and the delta H is positive or negative? So is this reaction endothermic or exothermic?
Exothermic?
Exo.
Uh, why exothermic?
Endo.
Yeah, it's endothermic. Okay, so you have a beaker here. The reaction happens inside the beaker. And you can see that the temperature drops sufficiently. What does it mean? It means when this reaction happens, it takes the energy from the surrounding and from the beaker. So that's why the temperature drops sufficiently. It means the reaction is endothermic. So the answer is either B or A. And you know the delta H for endothermic reaction is positive. So the answer would be B.
Could you explain again? I didn't understand.
Okay, so look, a reaction happens here between two substances. Okay?
Yes.
What happened to the temperature?
The temperature drops.
Drops. What does it mean? It means for happening this reaction, the energy is taken from surrounding. So always you are measuring the temperature of the surrounding. Okay? So what happens to the surrounding? The temperature of the surrounding is dropped. It means the energy has gone out of the surrounding. It means the energy gone into the system.
But like in the previous question, the temperature dropped, but we said it's exothermic.
No, I'm saying the temperature of the surrounding. Here it talks about the temperature of the surrounding. In the previous example, you had a block of the copper. The temperature of the copper decreased. What does it mean? It means it has lost the energy. So if you able to measure the temperature of the surrounding, what happens to the temperature of the surrounding? It increases. Okay. But the temperature of the system decreases. So be careful which temperature is given to you, the temperature of your object or the surrounding. In the chemical reaction, this is the physical example, okay? In the chemical reaction, always you are measuring the temperature of the surrounding, either the solution which reaction happens inside that, or the test tube, or the beaker, whatever you are measuring in the chemical reactions is the surrounding. So if the temperature of the surrounding is increased, it means your system has released the energy. The reaction has released the energy and temperature is increased. If the temperature of the surrounding decreased, it means your reaction has taken in the energy. So in this case, you can see that the temperature of the surrounding has decreased. It means the heat is transferred from the surrounding to the reactants. So it means the reaction was endothermic. Okay, is it clear?
Yes.
Okay. So let's go to the next question. Which one of the following statement is true for all exothermic reactions? They produce gases, they give out heat, they occur quickly, they involve combustion.
They give out heat.
Yeah, they give out heat. It's very easy. Next one, it says, if 500 joule of heat is added to 100-gram samples of each of the substances below, which will have the largest temperature increase? So the amount of heat which is given to the substances are same. The mass of each one are same. The only difference between them is the specific heat capacity. So which one shows the largest increase in temperature?
A.
The A. Yeah, we said if the specific heat capacity is small, it means by giving a small amount of heat, its temperature increases a lot. So smaller specific heat capacity, it means it will have more temperature increase or temperature change. So the answer is A. Also, you can find it from the equation. Okay. So what was the equation? Q equal mc delta t. Here the question asked about the delta t. So I rearrange this equation. I divide both sides by m over c. So m over c cancels here. It becomes q equal m and c. So you can see in this equation, the q is equal for all of them. The mass of all of them was equal. The only c is different. If the c is small, this fraction becomes big. So small heat, specific heat capacity means greater change in temperature. So the answer would be A. Question number 4. So temperature of 5-gram sample of the copper increased from 27 to 29. Calculate how much heat has been added to the system. So look, the temperature of the system is increasing. So it means the heat is added to the system. Okay, we are not measuring the temperature of surrounding here. Here we are measuring the temperature of the system. Okay, so it's very easy. We can simply use the equation Q equal mc delta T. The mass of the object was 5 gram, 5.0. I don't put the unit. Okay, let's put the unit. Gram times specific heat capacity is given here, 0.385 joule per gram per Kelvin times delta T. What is the delta T here? The delta T is T final minus T initial. So it's from 29 minus 27. It becomes 2. Okay. Here, you don't have any decimal point. Here also you don't have decimal point. So in the answer also we should not have any decimal point. So the temperature change is 2 degrees centigrade, which is equal to 2 Kelvin. So delta T is 2 Kelvin here. I have to multiply all of these to get the answer. Okay, this is the multiple choice question, so you cannot use the calculator here. So it means the calculations must be easy. 2 times 5 becomes 10. 10 times 0.385 becomes 3.85. So the answer is D. Okay. So the answer would be D, but actually it's not correct answer because here the number of the significant figure is 1. You have only one significant figure. So you must round the answer to one significant figure. So the answer must be 4. So if you had 4 here in the answer, the 4 would be the correct answer. But no, we don't have any other choices. So we take 3.85 joule as the answer. Question number 5 says, consider the specific heat capacity of the following metals. 1 kilogram sample of the metal at room temperature are heated by the same electrical heater for 10 minutes. Identify the metal which has the highest final temperature. So same question as number 3. Which one?
C.
The cadmium, yeah, C. It says heated by the same electrical heater for 10 minutes. And it means the Q which are given to any of them are equal to each other. The mass of them is equal to each other. Initial temperature is equal to each other because it's all at room temperature. So the one which has more temperature change will have highest final temperature, which is cadmium. Question number 6 says the specific heat capacity of the metallic mercury is 0.138 joule per gram per degree centigrade. If 100 joule of heat is added to 100 gram of sample of mercury at 25 degrees, what is the final temperature? So we have everything. We can find the final temperature. Let's at the beginning find the delta T, then we will find the final temperature. So our equation is Q equal mc delta T. So if we want to find the delta T, it becomes Q over mc. The Q energy which is given to the system is 100 joule. the mass of the mercury is 100 gram, and the specific heat capacity of the mercury is 0.138 joule per gram per Kelvin. So these 100 and 100 cancel out each other, and the delta T would be 7.25 degrees centigrade. Again, look at here. This one has 4 significant figures. This one has 4 significant figures. This one has 3 significant figures. So the answer is rounded to 3 significant. So this is the delta T. It means T final minus T initial is 7.25. Initial temperature is given since the mercury was at 25 degrees. So instead of T initial, I can write 25.0, and I can find T final becomes 7.25 minus 25.0. Okay, again here, this one has 2 decimal points, this one has 1 decimal point, so the answer must be rounded to 1 decimal point. The answer would be 32.3 degrees. So when you are multiplying and dividing several terms, the number of significant figures are important. The number of significant figures must be same as the smallest one. If you're adding or subtracting 2 terms, the number of the decimal point is important. The number of the decimal point in the answer must be same as the term which has a smaller decimal point. Okay, so this part was very easy, and if you had the physics this term, you probably have learned them in the physics class or maybe last year. Let's move on to the next topic. This is enthalpy changes and the direction of change. So what does direction of change mean? It means if you have a reactant and product together, the reaction goes from reactant to product, or it goes from the product to the reactant. Okay? What the reaction happens, or what these delta H and the sign of that, the negative or exothermic reaction and positive or endothermic reaction, can tell you if the reaction can happen or not. Always in the nature, as I have told you several times, the system wants to lower their energy. So they want to decrease their potential energy, because when their energy decreases, they become more stable. So you can understand that the direction of the change is in the direction of the lower stored energy. Direction of the lower stored energy means exothermic reaction, because in the exothermic reaction you have reactants, they are converting to the product and they release some energy. So if the energy of the reactant was here, they release some energy and they convert to the product. So the products have lower energy and it becomes more stable. Okay, as it's shown here. Okay. So if you slip from the ladder, obviously you don't go up, you fall down, because by falling down your potential energy decreases, and when you are on the floor you are become more stable. So the direction of any change in the nature is in the direction of increasing stability, means lowering the energy. So that's why in most of the reaction, the exothermic reaction is favored. So the reaction happens if that one is exothermic. Okay, but this is only part of the story. Another thing also is important, which we call it entropy. Entropy is shown by S. Entropy relates to the probability of any situation of the system. This concept is for HL students, so you will not study that one. In the nature, you can see that some endothermic reaction happens. The famous example is photosynthesis. The plants take the energy from the light and they convert carbon dioxide and the water to the sugar. So this reaction happens. In spite of that, the products has higher energy than the reactants. But another thing which happening here is that entropy of the system is increasing. That's why some endothermic reactions also can happen. So you should not confuse if you saw that some endothermic reactions also happen in the nature. Here is written, there are many examples of exothermic reaction and we generally expect a reaction to occur if it leads to a reduction in the enthalpy. Okay, so if the reaction decreases the enthalpy, it means if the reaction is exothermic, that reaction is reasonable to happen. But look at this one. This reaction is highly endothermic. It has a positive sign for delta H and the value of the delta H is very big. Okay? Look at what is written here. It says this reaction is extremely endothermic. Endothermic reactions are less common and occur when there is an increase in disorder of the system. So this is another important thing. For example, owing to the production of the gas, here a lot of gas is producing here. So it means the system becomes more disordered. Okay? So this is discussed in more detail later in this chapter, but it's not discussed for the SL student, it's for HL student. Okay? So the point here for SL student is that most of the reaction that happens must be exothermic. Why? Because they loses their energy, the energy content of the product decreases, and they become more stable. But you can see some endothermic reaction as well, because in some endothermic reaction, disorderness of the system increases. The reaction also wants to increase their disorderness. Okay, when we say two product or reactants relative to each other are stable or unstable, have lower energy or higher energy, it's very relative term. Okay? For example, look at here, if the hydrogen and oxygen react with each other to convert to these products, H2O and oxygen, the products are more stable than the reactants because the product has lower energy than H2 and O2, which are reactants. So this reaction can happen. And H2O easily converts to the water and O2. On the other side, H2 and O2 can convert to hydrogen peroxide, H2O2. Again, the hydrogen peroxide is more stable than the reactants that you had here by this one, delta H1. So this reaction also can happen. So we can say H2O2 is more stable than H2 plus O2. But the point is they are relative to each other more stable. If you want to compare H2O2 to water and oxygen, obviously water and oxygen are more stable. So H2O2 can easily convert to that one. So the point of this one is that when we are talking about the stability of any system, it's relative to each other. Okay? So we can say H2O2 is stable, but it's relative to these ones. Relative to these ones, they are not stable. Okay? Any question? Okay, so if you don't have question, let's move on to the next topic. It says measuring enthalpy change of combustion. What was combustion? Who remembers what is combustion? Combustion is burning. Okay, when you burn something and it releases heat and light, we say the combustion reaction. Okay, so we want to measure the energy change of combustion reaction. So the energy change, the reaction must be exothermic because we are talking about the combustion. So look at the enthalpy change of combustion. It says the standard enthalpy change of combustion, which we show it by delta HC, which means combustion, and we put the note here, which means we are measuring under the standard conditions. Okay, I think you are remembering what was standard conditions. The concentration must be 1 mole per decimeter cube. The pressure is 1 atmosphere or 100 times 10 to the power of 3 Pascal. And the temperature assumes to be 25 if it is not mentioned there. Okay. So under these conditions, the standard enthalpy change of combustion is enthalpy change for the combustion or for complete combustion of 1 mole of substance in its standard state in excess oxygen under the standard conditions. So, for example, if you want to measure the standard enthalpy change of combustion of HCH4 methane, you must have enough oxygen, O2, okay, to burn it to its product, which is CO2 and H2O. But what are important in these definitions? All of these substances must be in their standard state. The standard state of the methane under the standard condition is gas. A standard state of the oxygen under the standard condition is gas. At room temperature, the pressure of 1 atmosphere, the oxygen is gas. Okay, and the oxygen must be excess. So we assume that all of the methane is burning, and the amount of the methane that we must have here is for 1 mole. If you have 2 mole methane, the amount of heat which is released here, you must divide it by 2, because the standard enthalpy change is measured for only 1 mole of substance. How we can measure a standard enthalpy of combustion, delta Hc? There is one famous method for measuring the standard enthalpy of combustion, and that is calorimetry. Okay, calorimetry comes from the calorie. Calorie is the unit of energy. Okay, so we have, for example, 10 calorie, 20 calories. So it's the unit of the energy because we are measuring the amount of energy here to this device. This device is called calorimeter. So how the calorimeter works? Suppose you want to measure the standard enthalpy combustion of ethanol. The ethanol is alcohol. If you burn the alcohol, it releases a lot of heat. Okay, so we can find the standard enthalpy change for burning methanol or for combustion of the ethanol. So this device, which you see here, is calorimeter, and we use that one for measuring the delta H of combustion of ethanol. So what do you have inside this burner? Here you have ethanol. You burn the ethanol. So you know that the burning or combustion is exothermic reaction. So what happened to the heat? It releases the heat. Where the heat goes? The heat goes into the surrounding. One of the surrounding is the beaker that you have above this one, and there is water inside that one. So you have the water inside the beaker. So some part of this heat which is released transfers to the water. What happens to the temperature of the water? Temperature of the water obviously increases. So from the amount of the change in the temperature of the water, we can find how much energy is transferred to the water, which is equal to the amount of energy which released by the combustion of the ethanol. So here we know how much water is inside that one because we have measured that one. We put the water here. We know specific heat capacity of the water. By the thermometer, we can find initial and final temperature of the water before burning and after burning of the ethanol. So we can find delta T. So if we multiply all of these mass by specific heat capacity by the temperature of the water, we can find the Q. But what is this Q? This Q is the amount of heat which transferred to the water, which is equal, Q of water is equal to negative Q of ethanol. Why they have opposite sign? So if the Q, for example, is 23 joule, the Q of ethanol would be negative 20 joule. Why
چون که
the,
اتانول داره انرژی میده
okay?
دیگه باید نگاتیو باشه
Yeah, because
اکسوترمیک باشه
no, because the ethanol is giving out the energy, okay? The water is taken in the energy. So one process is exothermic, the other process is endothermic. So their sign is opposite to each other. But what is another problem that we have with this equation? Okay, their sign must be opposite. Okay? There is no problem. The water gains the energy, ethanol loses the energy. Ethanol releases the energy. So their sign must be different. But what's the problem with this equation again?
همه انرژی نمیره به آب
Exactly. So not all of the energy transfers to the water. Some of the energy transfers to the air that you have here. Some energy transfers to this container. So the container is made from the copper. That's why to this system we call it copper calorimeter. Okay. So, and what do we have here? These two walls, okay, they are insulator. What is insulator? Insulator is a substance that don't transfer the heat, or its heat conductivity is very low. So it doesn't let the Q or the heat to go to the surrounding. But we cannot guarantee that we prevent the heat to go to the area around the calorimeter by 100%. But we decrease its amount by a large quantity. So the problem is that not all of this heat which is released transfers to the water. Some of them even transfers to the copper calorimeter here. So this equation, we can use it by some assumption. And the assumption is that all of the heat which is produced by the ethanol is transferred to the water. And we know that this is not quite correct assumptions, but we don't have any other choice. We have to use that one, but it gives us the good approximation of the amount of heat which is released by the burning ethanol. Sometimes they also tells you how the temperature of these copper calorimeter is changed. In that case, the Q of the water, sorry, the Q of ethanol would be equal to the negative temperature or heat which is transferred to the water plus heat which is transferred to the copper calorimeter. Okay, so if the information for the copper calorimeter is given, also we can have it here. So this one is better estimation for amount of heat which is released by the burning ethanol. Okay, but I'm not written here that I have measured delta H combustion for ethanol. I just written that I have Q of ethanol. What is the difference between these two? The heat which is released by ethanol and the enthalpy change of combustion of ethanol. What is the difference between them? The Q of ethanol is the amount of heat which is given out by burning the ethanol. But the delta H of combustion, if you remember, we have measured it for 1 mole. Okay, this one must be amount of heat which is released by burning 1 mole of substance. But the Q doesn't guarantee that you have burned 1 mole of substance. So that's why you must identify how much methanol is burned here. So you can find the mass of the methanol which is burned here. If you divide it by the molar mass of the methanol, you can understand how many mole of ethanol is burned there. So if, for example, 3 mole of ethanol is burned here, you have to divide this one by 3 to find the delta H. If 4 mole of methanol is burned here, you have to divide this one by 4 to find the delta H. So I can write the delta H of combustion equal to the negative Q of water divided by N. What is the N? N is the mole of the substance which is burned. Okay, mole of ethanol which is burned. But another question here, how can I understand how many mole of ethanol I have burned here inside this experiment? The amount of temperature gives you the Q of the water. So the Q of the water is the mass of water times specific heat capacity of the water times temperature change of the water. This gives you Q of water, which is negative of that. Negative of that would be Q of ethanol. But how do you know how much ethanol has burned here? So this amount of heat which we are measuring is for how many mole of ethanol? Is it for 1 mole of ethanol, 2 mole of ethanol? How we can understand how many moles of ethanol is burned here? It's very easy. Just think about that one a little bit. How you can measure the mole?
Mass divided by molar mass?
Mass over molar mass. You have the molar mass of ethanol. You know its molecular formula, so you can easily find its molar mass. So the point is how you know how many gram of ethanol has burned. Suppose you are going to the lab and you want to do this experiment. How do you know how much methanol is or ethanol is burned? Any suggestion?
You measure it yourself.
Okay, how do I measure it? How do I measure the mass of the ethanol which is burned here?
First, we will weight the original mass before the heat is applied,
Okay.
and then we're gonna measure the mass after the heat is applied.
After, yeah. So at the beginning of the experiment, before starting the experiment, you have to measure the mass of this burner, which contains the ethanol. Suppose the mass is 43 gram. You burn ethanol, okay, after, for example, 2 minutes, you stop burning. The heat transfers to the water, you have the temperature change of the water, you have the mass of the water here, so you can find mass times specific heat capacity times delta T, you can find Q of the water. Then you take this burner again and you weight that one. Suppose its weight becomes, for example, 35 gram. If you subtract this one, you can see that 8 gram of ethanol has burned. So by measuring the mass of the burner, which contains your fuel, in this case ethanol, before burning and after burning, you can know how many gram of that one is burned. If you divide that one by the molar mass, you can understand how many mole of that one is burned. So the Q which you get here from the temperature of change of the water must be divided by this mole to find the delta H for 1 mole. So the unit is joule per mole. The unit of the delta H is joule per mole.